Alright, welcome to Lab 2 for Physics 2211, so if you're on manga. For the purpose of this lab, it'll be to make two separate models of an object falling. One model will have gravity acting on it, and the other one will have gravity and drag. We're going to make these models in GlowScript and compare them to the graph of an actual object, and that graph will be getting through the tracker software. And later on in this lab, you'll see that accounting for drag brought us closer to predicting the position in real life. It wasn't 100% accurate, but it was a lot closer. And also you'll see that changing the initial velocity does not affect the terminal velocity at all. Concepts used in this lab will be Newton's second law, with a force acting on the object, unlike the last lab. And these forces will be gravity and drag. Gravity is given as mass times acceleration due to gravity, and drag is given as proportionality constant times magnitude of velocity squared times j hat. And the equation to calculate the final velocity will be a relevant equation. Calculating the final velocity, which is velocity update equation, will be v final is equal to v initial plus f net over m times delta t. And f net will be in terms of gravity and drag. So we'll move on to our tracker demo right here. Let me restart the video. So tracker, you can see right here that I was holding the ball one frame, and then the next frame, as soon as I let go, I started plotting the point, and I kept going to the frame right before the ball hit the ground, and you can see all these plotted right here on the right side, as well as the actual table of the specific points right below it. And then we'll go back to GlowScript, sorry. So through our GlowScript code, I'll go through the changes I made. So first change was mass, which is 41 grams. The initial position, initial velocity is 0. The start time and delta t, which we also got the tracker, 0.2 and 0.033. And this block of code has no drag, so the proportionality constant is 0. And as such, F net is only affected by the force of gravity, which is mass times acceleration due to gravity times j hat. And then we have the position and velocity update equations right here as well. Final velocity is equal to initial velocity plus f net over m times delta t, and position is equal to initial position plus velocity times delta t. And no other changes were made in that block until we get to the next block, where we did account for drag, and you can see that there are proportionality constant. Everything before the proportionality constant for this block was the same. The constant itself is different from 0 to 0.05, and in the block and in the loop, we account for the force of drag as well. The constant times the magnitude of velocity squared times j hat, and everything else remains the same, including the velocity and position update formulas. And you can see that running the program, we get position and velocity for just gravity and position and velocity for gravity and drag. And we'll get back to our PowerPoint. So right here, comparing the data, as you can see from this graph on the right side, that the model that accounted for drag was a lot closer to predicting the position in real life in comparison to the model that did not account for drag. The model that did not account for drag was a lot farther off, and the one that did account for drag was not entirely accurate as well, and we'll get into sources of error as to why that may be. So these sources include the actual drag force, the forces that we had. The drag force could have been improperly calculated, as the proportionality constant was, I found it out by trial and error, so that could be incorrect. And also there were more forces acting on the ball that we did not account for in our model as well. So further, what does it mean? The terminal velocity refers to a speed that an object can reach when falling, when the drag force and the gravity force are equal and opposite. You can see this in our velocity versus time graph for the model that accounted for drag, and I can show you that right now. Going back to GlowScript. So as you can see, the model that accounted for drag right here in the velocity versus time, you can see the graph start to level out, and even in the position versus time, the slope stops increasing in magnitude. And we'll get back to the PowerPoint, go over the what if. So if the object were initially thrown downward, then the only thing to change would be the initial velocity. Terminal velocity would stay the same, as it does not depend on the initial velocity, and I can show you that in the GlowScript as well. Oh, excuse me. There we go. So if we edit it, and I scroll down to the block of code where we had the drag being accounted for, and I change this to -1, so the ball being thrown downwards now, and then we run the program. The position versus time changes, but the velocity versus time, you can see it remains the same, and it starts to level out in the same area as well. So the terminal velocity does not change.